Hey, here we're going to talk about the volume of a rotation created, and we're going to talk about that volume in terms of the shell method. We have seen disk and washer method, which are the same premise, but the shell method is definitely a different idea. Alright, so as I said, the disk and the washer basically stack circles on top of each other. So each little circle has its own little area, and when you put them all together, you get this big three-dimensional stack, so you can have a volume. Now the shell method over here does it a little bit different. It still goes around an axis of rotation, and it still creates a three-dimensional figure, but the way we're going to calculate it, instead of having solid flat circles, we're going to have these cylinders or shells. So we're creating basically like a set of cans inside of each other. So if you had some type of nested stacking system, kind of like those dolls that go inside one another, that's what the shell method would be like. You could think about going to the grocery store and picking up all different sizes of cans, taking the top and bottom off and sticking them inside of each other, and maybe you could get a perfect fit, and you could get this band or shell that we have here. So just a little bit about a cylinder. We're going for the shell of the cylinder, the band. So basically, if we had a can, we could have the surface area of that can, which is a circular cylinder with a top and a bottom. So that surface area is two circles, the top and the bottom, 2 pi r squared, plus the side. Well, the side is a length times a width if you unroll it, and that length would be 2 pi r. That would be the circumference of the circle, and the height would be the other part of the circle. So the area of each shell will be 2 pi rh. So basically that is creating a rectangle around a circle. So that's the shell, and then the h gives it the height. Okay, so that's the part that we're really going to be focused in on. So let's see what that looks like here. So it's a little bit different. We're going to be rotating around the y-axis first, and when we do the y-axis or a vertical line, we want everything in terms of x. Now that's the opposite of what we did with the disk and washer method. So the idea here is, if you can see the little band cylinder we have around here, there is a radius. Let's use a different color. There is a radius, which in this case goes out to x, and there is a height that we would have as well. Green on yellow makes green, blue on yellow makes green, so they look the same now. My fault. Let's see if this helps. That just messes it up. Pause. Okay, that's a little bit better. So basically, like we said, we want 2 pi rh, so we need a radius for our cylinder, and we need a height for it. And we want everything to be in terms of x when we're done here. So that's what we're going to focus on. So we still got our endpoints, but they'll be in terms of x if we're going around the y-axis. So let's try and see what happens here in an example. So it says we're going to find the volume when we rotate this thing around the y-axis. So I'm going to go ahead and write out the formula. Volume equals, I'm going to go ahead and put the 2 pi outside from A to B. And we need an R, we need an H, and that'll be in dx. So A, B, R, and H are all going to be in terms of x. So I've got this figure here. It's in the first quadrant. It goes over to x equals square root of 3. And it's between the x-axis and the line y equals square root of x squared plus 1. And we're going to take that around the y-axis, we said. So you can kind of see that it'd be a bunch of cans inside of each other if we drew the cylinders. So what we need here is a couple things. We need bounds. So the region that we're going to rotate, let's get a little bit darker color. The region we're going to rotate in terms of x goes from 0 all the way to square root of 3. So that's my A and that's my B. So when I write it out, volume equals 2 pi. It'll go from 0 to square root of 3. That's the region I'm going to rotate. So the radius, this is the interesting thing. the radius is going to vary where we want to go, because in the center here we will have some small cans with a little height and a little radius, and as we move further out we'll have some bigger cans with a bigger radius and a bigger height, and that's just for this problem. So the radius will be out from the center out to a point on the cylinder, and we're just going to call that radius x. Okay. We said it needs to be in terms of the x value, but as we move out across the x-axis, that would be the actual radius from the origin here. So if I came out to 1, that would be, if I came out to x equals 1, that would be the radius of the cylinder. If I came out to 1.5, if that keeps me within the square root of 3, that's what the radius would be. So the radius will just be x. And if you're going around the x or the y-axis, it will usually just be a single variable. Now the height in this thing is going to come up from the bottom to the top, and we want it in terms of x, so that would be the function. That would be the height from the base of this thing up to the actual function. So the height of it will be square root of x squared plus 1. So that is what's going to give me the volume if I take this thing using the shell method. So once again, the radius is x, and the actual function in this case is the height. Okay, so I think we're going to need to do a u substitution here. U sub would give me u is x squared plus 1. du is 2x dx. So 1/2 du equals x dx. So we will use that as a substitution. We'll have the volume is 2 pi. We'll have our integral. So we're going to replace x dx with 1/2 du. And we're going to place x squared plus 1 with u, so that'll be the square root of u, or u to the 1/2. So as we do that, and we take the integration in terms of u, u will go up to 3/2. I'm getting a little too small here, I think. Let's get my eraser out, and I'll write a little bit bigger for that. U to the 3/2. And when we divide by 3/2, it'll be times 2/3. So when I go back to x, it'll be, looks like 4/3 pi, and then x squared plus 1 to the 3/2, and then I'm going to plug in 0 and square root of 3. So let's see here. When I plug in square root of 3, I'm running out of room. X equals square root of 3. I will get that square, so that'll be 4/3 pi, and it will be times 4 to the 3/2, which will be 2. That'll be times 8. You can use a calculator there. And if I let x equal 0, then I'll have 1, so it'll look like 4/3 pi. So an exact number here would be 4/3 pi times 7, because I would have 1 less. So that would be 28/3 pi. That would be an exact number. And let me put in the calculator. 28 divided by 3 times pi. Looks like around 29.32. Okay, now we could do this with a different method. Just a little bit of talk after we've got this answer. The difference between using a shell here and the washer disc would be, if you were to look at this thing on the y-axis from 0 to 1, you could use a disk if you go around the y-axis because there's no gap there. So use a disk. You wouldn't have to subtract the inner radius. But once you got to 1, y equals 1 up to y equals 2, you would have to switch that to a washer method. So if you were to go around the y-axis and use the disk washer method, you'd have to break it into two separate integrals. One from 0 to 1 using the disk method, and a second one from 1 to 2 using the washer method. So the cylinder method here, cylinder or shell, kind of allows you the ability to eliminate that part and have those gaps in places and not in others. All right.